Are you a data scientist? Do your tools make it easy to track your experiments, deploy to a machine learning model to production, and manage a GPU cluster? This free book from O'Reilly can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world.
This is kind of a follow-up to Bryce's videos on deep learning. So deep learning is kind of a big thing at the moment, and there's some disagreement between research over whether this is going to be this is it. This is the big thing that's going to change everything, or whether this is another flash in the pan like artificial neural networks were in the 80s. Everyone got very excited and they got quite a good results, and then they realised that they couldn't solve all the problems with them. They don't know. For what it's worth, these are a big deal, I think.
Let's talk about convoluted neural networks. Have I said that right?
Convolutional neural networks.
Ah, right, okay.
They combine both deep neural networks, which is what Bryce was talking about, and kernel convolutions, which is what I talked about in a previous video. So I would thoroughly recommend people watch that video. You know, it's an entertaining host, right? So, but because if you don't know what a kernel convolution is, this isn't going to make much sense to you. Okay, so watch that video first.
So that's the kernel convolutions we did on graphics and things like Sobel operators.
Yeah, Sobel operators, Gaussian blurs and things like this. Okay, Sobel operator in particular and edge detection. So if we think back to a traditional artificial neural network, okay, what we've got is we've got some kind of input we're trying to learn. Okay, we've got some hidden layers, right, and then we've got some output layers. Maybe there's just one, I don't know. Okay, and these are fully connected, so we have lots of connections from here and here and here, and then these are connected to here, and so on. I'm just drawing in a few of them, and then these are all connected to the end. Okay, now using Bryce's analogy, we were talking about house prices. Okay, so this would be something like number of bedrooms, and this would be something like if has it got a pool, and this would be, you know, what floor space is it, and has it got a good garden, and so on. Lots of these, okay, lots of inner nodes that we don't really care about particularly, or I don't. Right, but and so on and so forth, and then finally at the end we have a house price. Now what this house price is a complicated function of these inputs. It's complicated because this node here is some linear or non-linear now combination of these. Okay, so a bit of this, plus a bit of this, plus a bit of this, plus a bit of this, through some non-linearity function. This is a different combination of these. This, again, different combination of these, and so on. Right? And then this is a different combination of these. So you can see you're building up some kind of level of abstraction here, where you've got combinations of combinations. Okay? And that function is very complicated. When Bryce talked about a black box, in some ways that's exactly what it is, because we can't look at these individual weights and say, well, that's got 0.2 of this one, so that must mean this, because we just don't know what it means. Right? In the grand scheme of things, in this whole network, we don't know what that individual weight means. Okay? And to be honest, we might not even care that much. What we really care about is how well does it predict house price? How accurate is that based on that for a different input? So we change this, read the output. Is it good? Yes, brilliant. Okay. Now, for images, which is obviously what I spend most of my time around, this is a start, but it's not very useful to me. If you think that this is our inputs, okay, and I give you a picture of a house, and I say, right, tell me how much this house is worth, okay, well, what? So how do I, okay, so there's two things I could do, right? First of all, is I could try and calculate things like number of bedrooms and stuff based on the image and put them in here. In some way, I'd be calculating some features and then I'd be putting them in here and learning on those features. That is quite a smart way of doing it, because apart from that's obviously quite difficult. It's smart because we don't have to have that many more neurons. In anything, we can actually use the same network as we used before for our model on our house. All we have to do is work out the bit of code that does the image analysis. Now, anyone that's tried to find out the number of rooms in a house based only on one picture of the outside of the house will tell me that that can't be done, right? That's hard, okay? So you could naively think what we could do instead is just put the image in here, make this the first pixel, and this the second pixel, and this is the third pixel, and so on, okay? Then, this has got all the information it could ever need, right? But that's the problem, okay? 7 megapixel image, that's 7 million input nodes. Let's say we have 7 million nodes on the next layer, each one connects to each other one, you can see that that's just going to melt my computer. It's not even going to try and create it. It's too much information. Okay? That's why we downsample our space a little bit. What we would usually do is calculate some small subset of features, and then we will put them in at this end. So that's quite important. So traditional machine learning is done a bit like that. So Michelle's done some videos on this. Calculate some features about someone's face and put that into some machine learning algorithm. What you don't do is try and put the machine learning algorithm just on the face, because there's too much information there. until now, okay? Right? That's where convolutional neural networks step in. So convolutional neural networks replace each of these nodes with a kernel convolution, so like a Sobel edge detector, okay? Now, so instead of what I would have done before, which was run a Sobel over something and then machine learn on that, I just give this the opportunity to learn which features are interesting. Maybe it is an edge detection, maybe it's a corner detection, maybe it's something that highlights whatever's in the middle of the picture, okay? Or something that highlights the top left-hand corner. It doesn't really matter. And the point is, I don't know what they are, right? If I give you, 2,000 pictures of houses and ask you to predict house price based on the pictures, right? I don't know for sure. I can guess that it might be how many windows it has and things like this, but I don't know for sure, okay? And a computer can brute force through those things much quicker than I can and tell me, okay? And then I can both predict it and I can look back and say, oh, it was windows after all. So let's imagine that what we have is our image, okay? So I'm going to move away from the house analogy now because I'm going to have to draw a lot of pictures of houses if I do that. Okay, so let's talk about how CNN works and why it's useful. So we have an image of something. Now, I have seen convolutional neural networks used for non-images, but for now we'll just talk about images. This is a picture of, let's say, me. It's, it's not a great likeness, but I'll stick by it. Now, there are 3 channels here, okay? So this is actually a 3D volume in some sense. Remember when we talked about 3D images, you could view RGB as in some sense 3D. So the first plane is R, G, and B, or vice versa. What we do is, if we performed a Sobel edge detection on this, what it would do is produce another image that was slightly smaller than this and only 1 deep. So hypothetically, it would be another image where the edges, let's say the horizontal edges, were highlighted. So it would kind of look like that or something, I don't know, some half of my face where the horizontal edges are highlighted, okay? It's not a great diagram. But there would only be 1 output because Sobel just outputs a number between 0 and 255, as long as you scale it, okay? Now the problem is that I don't know that Sobel's the best thing for this task. Okay? It might be, right? It might be useful to detect edges on houses to work out what their price are, or if you want to detect faces, to detect the sides of the faces. That kind of makes sense. On the other hand, it's going to produce a lot of erroneous bits. If I'm sitting in front of a tree, there's going to be loads of edge stuff going on there that I don't care about. In a convolutional neural network, what we do is we do, let's say, 60 of these on the first layer. So we have 1, and then behind it we have another 1, behind it we have another 1, behind it we have another 1, and so on, going this way. So the first one will be some convolution process applied to this whole image that takes 3 input channels and outputs 1 output channel. The next one will be a different kernel convolution operation. So each of these will have a different kernel. Those are our weights, those are these values here, instead of our analogy back to normal learning. And so let's say we have 60 of those, or 64 of those. Okay. One of them might be detecting edges, one of them might be detecting corners. And then we use them as our features for learning. Now that's a start, but this is deep learning now, right? So what do we do now? Well, what we now do is we do more features based on these features. So we find combinations of corners, combinations of edges that make something interesting. My face is not just a circle of edges. What it is a number of corners and edges and bits of texture and things, all in a specific shape that is unique to, well, certainly to a human face, but even unique to me, right? These are capable of distinguishing between different people. So this kernel window will go down to this pixel here, okay? So this will slide about this image and produce this output image. And then the next one will do the same, and the next one will do the same. Then we do the same thing on this one. Let me do it in a different pen so we can see better. Here's my red kernel convolution, and this slides about and produces another image, which is a slight combination of maybe corners and edges or something. I mean, at this second level, it's not going to be too abstract, but we'll get the idea. Okay, so there's going to be some sort of shape that's going to be it's not going to make much sense to us, but it'll make some sense to this machine. And there'll be another set of these, so there'll be lots of these, right, going back. All of these will look different and be some different representation of my face transformed in some way to be useful. Okay? And again, I haven't picked these. These have been learned just like a normal deep learning algorithm. So I haven't had to say, I definitely think edges are important for this, because I don't know for sure. So this goes on, and we keep doing this. And sometimes we also downsample the size of these images just to save memory. Okay, but we won't dwell on that too much. And because of the way that we downsample, and the way that sometimes these convolution operations slightly shrink the image, because they don't go all the way to the edge. Right? If you've got a 5x5 kernel, you can't go to the edge 2 pixels because you're going off the edge. So we don't worry about that. We just get slightly smaller. In the end, we end up with a much smaller image and lots of features going all the way back. So these are my different convolutions of convolutions of convolutions of convolutions. And each one will look different and represent something different, and we don't know what that is. So this one could be highlighted when there's a face in the middle, or it could be dark when there isn't. This one might be highlighted when there's an ear at a certain position, and so on. Eventually, these will get down to being just 1 pixel and very, very long. So essentially what we've done there is we've completely removed the spatial dimension. There's no more spatial information left. We don't know where anything is, but we know what it is because it's listed in all these features. These now are our neurons at the end. So we have a couple more layers that point to these, and then finally we have one at the end that says, is this a picture of Mike's face? Okay, and it produces a 1 if it is and a 0 if it isn't. And then what we do is just like a normal network, we train it. So we say, here's a picture of me, okay? So this should be a 1, and let's say it's a 0.5, okay, because it's kind of random. So we adjust these weights, and we adjust the weights inside all these kernel convolutions.
So does that adjustment happen manually?
No, it happens using a, well, it's coded in, but it's usually performed by a library, and it's using a process called backpropagation. So what we do is we basically predict what direction we have to move the weights in to improve our output, and then we move them ever so slightly in that direction. And we have to do it in reverse order. Because these ones depend on these ones, depend on these ones, and vice versa, what we do is we say, well, look, given that I've said it's 0.5% chance of Mike and we want a 1, how do I change these weights here to get slightly closer to 1? And I do it. And then I say, how do I change these again to do even better? And so on, and I work my way back, okay? That kind of maths we're not going to go into, right? A lot of these things are implemented in libraries. So as a researcher, I mean, much as I'd like to implement some of these things, it takes quite a long time just because programming takes a while, right? And it's better for me just to apply these things and get good results than it is for me to reinvent the wheel all the time, constantly. If everyone was programming the same things over and over again, no one would get anything done, right? Because I'd have to start by programming up Linux to get, I'm not claiming I can, by the way, and so on. So, you know, let's not reinvent the wheel. So I do this, I send them, let's say 1,000 pictures, 500 of which are me, you know, so I've been to a photo shoot or something, right? And 500 of which are not. And I train it so the convolutions and these weights on the output are such that it gets 1 when there's a picture of me and 0 when it isn't, okay? And then I can look at these convolutions and say, what is it about me that's distinctive? Right? And it's probably going to be finding you know, weird shapes on my face, right? Because it's a bit of a weird shape. So things that are unique to me. Now, in a more general situation, there's a big database called ImageNet, right? They have a competition every year to see who can classify these images the best. So dogs, cats, planes, trees, and so on. Okay, they're all in there, and there's 1,000 or so images of each, right? So we have a really big network that's much bigger than this little one I drew. And we say, right, let's throw millions of images at this, right? Thousands of cats, thousands of dogs, and we have lots more outputs than just the one. And we say, what is it? And it's a dog, and it is. Convolutional neural networks have been around for a little while, but they've really started to be big in about 2012 when someone came along, applied one of these to ImageNet, and got incredible results, and so on and so forth. And now there's this big push, and everyone's trying to get even better results and even better results. Now, I work on more of the applied end of computer science, so I'm more interested in how this affects plant science and things like this. So that's what we're working on. But the kind of results we're seeing are really, really impressive. So, I mean, case in point, I've done some root tip detection, so detection of root tips in images, right, of plants. And I've got some software that I've already programmed, and I've kind of done a low-level feature detector approach to detecting root tips, and it's about 70%. Okay, which is what you would expect, because maybe some root hair gets confused as a root tip, or a bit of blotch of dirt, or maybe there's just 2 root tips really close together and it gets confused. Okay? The CNN that I trained is 98% accurate, and it finds them with 99% accuracy. It doesn't make many mistakes, right? And that's over thousands of images.
So does that mean the work you've done already just goes out the window?
Yeah. No, to an extent, yes. So to an extent, no. You need expertise to be able to craft a network and train it and prepare the images. And there's obviously work to be done. And there's some disagreement over how much of a problem you can solve with a convolutional neural network, right? So there are lots more things you can do with roots beyond finding tips. Can you do all of them with a convolutional neural network? I don't know, we'll see. I'll be trying, but we'll see, okay? Maybe not. So maybe what you do is you use this as a tool, just like other machine learning algorithms, within a package that does lots of other things as well. On the other hand, if you're just doing cat and dog detection, you might as well use the CNN because it's going to do better than everything else.
The other purpose for which the botnet can use its bots is for distributed computing.
Okay. Now, some objects obviously are more amenable to this than others, but the more images we get, the better it is. There's no depth involved here at all. Okay?